Welcome back to the deep dive. I want you to start today by just picturing a timeline in your head.
Okay.
Usually when we talk about the future, the real sci-fi stuff, that timeline is, well, it's always kind of foggy, isn't it?
It's blurry on purpose. It's 10 years away.
Always 10 years away. Or, in the coming
Or
decades.
my favorite, just eventually.
Eventually. It gives us a safe distance, right? Lets us keep our current view of the world totally intact because the real disruption is always just, a little bit over the horizon.
It's the comfort of ambiguity. As long as the flying cars and the robot butlers are always someday, we don't really have to grapple with what that means for our economy or our lives today.
Exactly. But today, we're looking at a source that it takes a giant red marker and circles three very, very specific years on the calendar.
And they're not decades away?
Not even close. They're right on top of us. We're talking about 2027, 2028, and 2029.
And we should be clear, the subject here isn't like a new iPhone with a slightly better camera.
Yeah.
It is the fundamental restructuring of the human labor market, period. All of it, via humanoid robotics.
So today, we are unpacking what we're calling the Optimus timeline. And to set the scene, our main source material anchors us to this really specific moment in time.
I love when we can do this.
It's Saturday, February 14th, 2026, Valentine's Day.
A very romantic date for a technological revolution to be announced.
Right. While pretty much the rest of the world was, buying roses or fighting for dinner reservations, a completely different kind of exchange was happening on X.
The platform formerly known as Twitter.
And it involves two absolute heavy hitters. On one side, you have Cathie and the research team at ARK Invest.
And on the other side, Elon Musk.
And the context here is just so important.
It's everything. ARK isn't just, posting memes or hot takes. They're sharing a really dense, really thoughtful piece of research.
Super dense.
And it's about the sheer, almost mathematical difficulty of creating a humanoid robot that can function in the real world.
They're basically trying to quantify the chaos of the physical world.
Yeah.
And frankly, if you're an engineer, the way they lay it out is actually kind of terrifying.
It is.
We are going to get deep into their numbers in just a minute. Specifically, this one claim that building a humanoid robot is 200,000 times harder than building a self-driving car.
That's the headline number.
That number just stopped me in my tracks. But it's actually Musk's response to this research that gives us our mission, for this whole deep dive.
Right. He doesn't just agree or say, cool research. He gives a forecast.
And it is so specific, so precise.
It was a trademark Musk reply. You know the kind. Super compressed, incredibly high stakes.
And he put a clock on it.
He put a very specific clock on it.
I have it right here in front of me. He writes, "It will begin to transform things in 2027, be obvious in 2028, and have a massive impact by 2029.
3 sentences.
Years.
And trillions upon trillions of dollars of implication packed into that one post.
That is the timeline we're going to stress test today. We are sitting here right now in early 2026. He is saying this whole transformation starts next year.
That is the claim. And I think for you, for the listener, the immediate reaction should be skepticism. It has to be.
Of course.
We've heard aggressive timelines from him before. I mean, we've been hearing that full self-driving is a year away for a long time now.
That's a very fair point.
But the whole purpose of this deep dive isn't to just take the claim at face value. It's to look at the engineering that's supposedly underneath that claim.
Right.
Why did this timeline just get so much shorter? Why does Tesla seem to believe that the science project phase of this is over and the industrial ramp phase has actually begun?
What changed?
What changed? The answer seems to come down to some hard physics, some really clever manufacturing breakthroughs, and one very specific piece of anatomy that has, frankly, plagued roboticists for 50 years.
So, okay, let's peel back the layers here. To really understand if this timeline is, hype or if it's real, we have to first understand the sheer magnitude of the problem.
You have to respect the problem.
And ARK Invest, they dropped a number that at first glance just seems impossible. They claimed that building a scalable autonomous humanoid robot is 200,000 times more complex than scaling a robotaxi.
It's a staggering figure, just saying it out loud. 200,000.
It sounds like a made-up number.
Yeah.
It really does. I mean, we all know self-driving cars are hard, incredibly hard.
Oh, yeah. Decades and billions of dollars of effort.
So how can a robot walking around a factory would be 200,000 times harder than a car navigating a chaotic city street. A car is moving at 70 miles per hour. A robot is moving at, what, 3?
Intuitively, the car feels harder.
It feels way harder.
But intuition is almost always wrong when you get into robotics. ARK actually breaks this down into 5 specific dimensions of complexity. And when you walk through them one by one, you start to realize that a car is actually a very, very simple robot living in a surprisingly structured world.
Okay, so let's audit this math. Let's go through them. Dimension number 1 is something they call action bandwidth.
Action bandwidth.
Break that down for me. What does that actually mean?
Think about the user interface of a car. If you're an AI and you're trying to drive a car, what are your output options? What can you physically do?
Okay, I can turn the wheel left or right. I can hit the gas pedal. I can hit the brake.
Right.
Maybe use the turn signals, wipers, maybe shift gears if it's a manual. But that's about it.
Exactly. It's a very limited set of mechanical controls. You're basically just moving a rigid box on a 2-dimensional plane, which is the road. You speed up, you slow down, you turn left, you turn right. That is your entire action bandwidth.
Okay, simple enough. Now, compare that to a humanoid robot.
Well, first, it's not a rigid box.
Not at all.
Far from it. You have dozens and dozens of joints. You have a neck that can pan and tilt. You have shoulders, elbows, wrists that can all rotate and flex in multiple directions.
And then you get to the hands.
And then you get to the hands. You have, 3 joints in each finger, plus a thumb that has to oppose them all. Then you have a spine that can bend hips, knees, ankles. And here's the real kicker.
What's that?
They all have to move simultaneously and in perfect harmony.
Right. In a car, if I turn the steering wheel, it has 0 effect on the brakes.
Yeah.
They're totally independent systems.
Completely independent. But in a humanoid, if you just move your ankle 3 degrees to the left to adjust to uneven ground, your entire center of gravity shifts.
The whole system has to react.
Your hip has to immediately counterbalance. Your spine has to adjust its curvature. Your arms have to shift their weight, just to act as counterweights. If that entire system isn't perfectly synchronized down to the millisecond,
The robot just falls over.
it falls over. So the bandwidth of required actions per second just to stand still and maybe wave hello is exponentially higher than it is to drive a car at full speed down a highway.
So the control signal is just so much denser. It's like you're conducting a full symphony versus just, beating a single drum.
That's a great analogy. Orders of magnitude denser.
Okay.
And that complexity leads directly to the second dimension they identify,
Which is?
object interaction.
Okay, I'm guessing this is about what the machine does with all the stuff around it.
Precisely. A robotaxi, at its core, is an avoidance machine.
An avoidance machine. I like that.
Its golden rule, its prime directive is don't touch anything, don't touch the pedestrian, don't touch the curb, don't touch the other cars. It wants to live its entire life inside a protective bubble of empty space.
It's basically playing a giant game of dodgeball with reality.
It's playing dodgeball. That's perfect. Now, a humanoid is the exact opposite. It's an interaction machine.
Its whole purpose is to pop that bubble.
Its whole purpose is to break the bubble and engage with the world. It exists to touch things, to grab a door handle, to lift a box, to thread a tiny nut onto a bolt. It needs to understand things that a car never has to think about, like friction, texture, weight, and compliance.
And compliance means like how squishy something is.
Exactly. How much give does it have? So if a robotaxi sees a rock on the road, what does it do?
It drives around it.
It drives around it. It doesn't need to know if the walk is heavy or light, if it's solid granite, or if it's just a painted sponge that fell off a truck. It just avoids.
Right.
A humanoid has to be able to pick that object up, and it has to instantly know, before it even touches it, is this heavy? Will it crumble if I squeeze it? Is it slippery? Is it hot? The level of computation required to handle the world is infinitely more complex than the computation required to just avoid the world.
That is a fantastic distinction. Avoidance versus interaction. Okay, so what's the third dimension?
Scene entropy.
Entropy. That's
Right.
a measure of disorder. Right.
Okay.
Chaos.
Correct. And think about it. We often complain about traffic and how chaotic it is. But in the grand scheme of things, roads are actually highly structured environments.
I guess so. We have lanes painted on the ground.
We have signs that tell you the speed limit. We have traffic lights that tell everyone when to go and when to stop. We have a generally shared agreement on the rules of the road. It's what engineers would call a semi-structured environment.
Well, most of the time. Until you get to a four-way stop in the middle of a snowstorm with a confused tourist.
True, there are edge cases. But now compare even that chaotic intersection to a typical home, or a general-purpose factory floor, or a construction site.
That's pure chaos, high entropy.
Absolute chaos.
I'm just looking at my living room right now as you say that. There are dog toys on the floor. There's a shoe halfway under the couch. The lighting just changed because a cloud went over the sun.
And the geometry of that room changes constantly. Someone moves a chair, a cat runs across the room, a door that was fully open 5 minutes ago is now half closed.
The world is alive.
It is. A robotaxi can map a city, and that map stays relatively valid for days, maybe even weeks. A humanoid has to map a room, and 5 minutes later, that map is completely useless because you moved your coffee cup from the table to the counter.
So it can't rely on any pre-mapped data. It has to be figuring it all out live every single millisecond.
It's doing real-time reality resolution, and then you add the fourth dimension on top of that.
Which is task diversity.
Exactly. A robotaxi has one job. One single job.
Yeah, from point A to point B.
Transport a payload from coordinate A to coordinate B. That is it. It doesn't make coffee, it doesn't paint fences, it doesn't do your taxes.
And a humanoid robot.
A humanoid is the ultimate generalist. The entire expectation is that it can, say, unload a delivery truck, then walk inside and file some paperwork, then go to the break room and pour a cup of coffee, and then maybe, I don't know, go clean the toilet. The sheer number of distinct programs or skills it needs to be able to master is, for all practical purposes, infinite.
So it's the difference between, like, a grandmaster chess player who is an absolute genius at one thing and a really good handyman who can kind of fix your sink and wire a lamp and build a deck.
That's a perfect way to put it. And that brings us to the fifth and final dimension, which might be the most critical one, especially when it comes to safety.
And that is error tolerance.
The stakes.
The stakes of getting it wrong.
The stakes of precision. So let's do another comparison. If a self-driving car is, say, 6 inches off center in its lane, what happens?
Nothing, really. I mean, maybe the passenger feels a little uncomfortable for a second, but you're still safely in the lane.
Right. There's a slop factor. There's a margin for error. But now imagine a humanoid robot is holding a delicate wine glass, and its grip is off by just 6 millimeters.
Smashed glass everywhere.
Shattered. Or what if it's using a power drill next to a human worker on an assembly line and it miscalculates and slips?
That's a catastrophic injury.
It's a disaster. The margin for error in manipulation, in the fine motor skills of the hand, is absolutely microscopic compared to the margin for error in something like lane keeping.
So when ARK invests as 200,000x, they're not just, pulling a big scary number out of thin air.
Not at all.
They're taking action bandwidth, and they're multiplying it by the complexity of interaction, then multiplying that by the scene entropy, and then by task diversity, and finally by the incredibly strict requirements of error tolerance.
It's a compounding equation. It's multiplicative, not additive.
Hmm.
And it really explains why we had something like ChatGPT writing sonnets in computer code before we had a robot that could reliably fold a t-shirt.
The physical world is just that much harder than the digital world.
So much harder.
Which, okay, that brings us to the how.
Yeah.
If the math is that brutal, if the problem is that hard, and Elon Musk is out there saying transformation in 2027, which is basically tomorrow, they must have solved a very specific bottleneck.
A keystone problem.
And the source material we're looking at points to one single piece of anatomy that is the key to unlocking everything else.
The hand.
The hand. It always comes back to the hand.
It's the primary interface of civilization. Everything we do is mediated through our hands.
So explain this. Why is the hand the real mountain to climb? I mean, we've had robotic grippers in factories for, 40 years?
Longer, even.
Those big orange QUK arms that weld cars together, they have hands at the end of them.
No, they have clamps. They have pincers. They have specialized end effectors. That is not a hand.
What's the difference?
The human hand is, and this is not an exaggeration, arguably the most complex and elegant mechanical device in the known universe.
Wow.
You have roughly 27 to 28 degrees of freedom in your hand and wrist. That means distinct ways it can move, flex, extend, rotate. But the true genius of the human hand isn't just the number of joints in the fingers. It's the packaging.
The packaging, what do you mean by that?
I want you to do something. Look at your own hand. Now wiggle your fingers. Really flex them. Where are the muscles that are doing that work?
I mean, they're in my fingers, right? I can feel them moving.
Well, touch your fingers while you wiggle them. What you're feeling is mostly bone and tendon. Now, I want you to look at your forearm, put your other hand on your forearm, and wiggle your fingers again.
Oh, okay, well, the muscles in my arm are the things that are really moving.
Exactly. Evolution pulled off this brilliant engineering trick. It realized that muscles are heavy, they're bulky, they generate a lot of heat. If you put all the necessary muscles inside the fingers themselves, your fingers would be like fat
They'd
sausages.
be thick and slow and super clumsy.
Totally useless for fine manipulation. So biology did something clever. It moved the muscles upstream into the forearm where there's more space. And then it ran these high tensile cables, the tendons, down through the narrow channel of the wrist to control the fingers.
So it's basically a remote-controlled puppet system.
It's nature's own cable-driven puppet. It's a masterpiece of remote actuation. And this is what allows the hand itself to be incredibly light, slender, and fast, while still having the crushing grip strength provided by those massive muscles up in the arm.
So, okay, when Tesla or Boston Dynamics or anyone else tries to build a robotic hand, are they trying to do the same thing? With cables and tendons.
That's the great dilemma, because in the world of mechanical engineering, cable systems are a total nightmare.
Right.
They stretch over time, which ruins your calibration. They can snap under high load. They have a lot of friction, which creates control lag. They wear out and need to be replaced. It's a maintenance disaster.
Okay.
So modern roboticists try to avoid that. They try to put the motors directly in the hand right next to the joints they're controlling.
But then you have the packaging problem you mentioned.
You're right back to the packaging problem. You now need to fit for each finger a high-torque electric motor, a precision gearbox, and multiple sensors into a space that's about the size of a human knuckle.
And those motors have to be strong enough to, I don't know, crush a soda can, but also gentle and precise enough to pick up a single raw egg without breaking it.
And do that 1,000,000 times without overheating, without breaking. And this is the real kicker, the thing that separates a lab prototype from a product. You need to be able to manufacture them by the millions, cheaply and reliably.
And the source material makes a huge point of this. It says there was no supply chain for this kind of part.
Zero. Absolutely none. Think about it. If you want to build a car today, you can call up Bosch or Continental and just buy an anti-lock braking system off the shelf.
Right, you buy a steering rack, you buy tires. The parts exist in a catalog.
The parts exist. The global supply chain is mature. If you want to build a humanoid hand with this level of fidelity, the catalog is empty. There's no one to call. You can't buy the tiny high-torque actuators. You can't buy the custom gear systems.
So they had to go completely vertical.
It's vertical integration on steroids.
Yeah.
The source says Tesla is designing their own custom electric motors, their own tiny planetary gearboxes with almost zero backlash.
And backlash is that little bit of wiggle room in the gears, right? The thing that kills precision.
Exactly. It's the enemy of fine motor control. So they're designing the motors, the gearboxes, the tactile sensors, the control boards. They are building the entire stack from the silicon up simply because the industry to support them didn't exist.
This all leads into the discussion in the source about Gen 3. It says Optimus Gen 3, which is expected in early 2026, so basically right now in our podcast's timeline, is the critical inflection point.
It is. Gen 1 was the prototype they called Bumblebee. It was rough, exposed wires kind of pieced together.
Like a science fair project.
A very advanced one, but yes.
Oh.
Then Gen 2, which we saw a lot of last year, was much sleeker, faster, with much better hands, but still very clearly a mechanical object.
Right.
Gen 3 is the first iteration that is designed from the ground up for near-human dexterity. This is the version that is supposed to bridge that gap from a cool demo to an actual industrial labor platform.
And to explain just how hard it was to get to this point, Musk used this analogy that I think we really need to unpack.
The Cybertruck and Starship one.
Yes. He compared building the hand to a mix of the Cybertruck and the Starship. At first, that just sounded like a weird riddle to me. The hand is the Cybertruck plus the Starship, but at a micro scale. Let's break that apart.
Let's do it.
What does the Cybertruck represent in that equation?
The Cybertruck represents manufacturing innovation at scale.
Okay.
Remember, the truly hard part about the Cybertruck wasn't just the angular design. It was figuring out how the hell you build the thing. It's made of this ultra-hard, cold-rolled stainless steel.
Right. You can't stamp it in a press like a normal car hood. It would break the press.
It breaks, the stamping guy does. So they had to invent new methods for folding it with incredible precision. They had to pioneer the gigapress to cast these massive chunks of the vehicle's frame in one single go.
So the Cybertruck stands for the problem of, how do we build millions of these things efficiently when the very materials we're using are actively fighting us every step of the way?
Exactly. It represents solving production hell. Now, just apply that same thinking to the robot's hand. You're trying to mass produce an object with hundreds of tiny, high-precision, exotic parts.
It's not a luxury watch that you sell for $50,000, where a Swiss craftsman can sit there and file every little gear by hand.
No, this has to be a commodity part. You need to invent a nanopress. You need to design automation that builds the automation that builds the hand. It's a manufacturing nightmare.
Okay, so that's the Cybertruck side of the analogy.
Yeah.
Manufacturing hell. What about Starship? I mean, that's the biggest, most powerful rocket ever built.
Starship represents physics pushed to the absolute edge. Starship has to deal with the most extreme environments imaginable. Extreme heat during re-entry, extreme cryogenic temperatures for its fuel, extreme pressure, extreme vibration.
It lives on the razor's edge of what material science can even achieve before things melt or tear themselves apart.
Precisely. Now think about the hand again. The hand is a thermal nightmare.
Why thermal?
You have all these little electric motors generating waste heat, and they're all crammed into this tiny, sealed, often gloved enclosure, and they're working constantly. There's no airflow, there's no radiator.
So it's just getting hotter and hotter.
And if the hand gets too hot, the plastic components can deform, the sensors will fail, the lubricant in the gears can break down. You're pushing the physics of electromagnetism and thermodynamics to their absolute limit in an incredibly confined space.
So the hand is manufacturing hell meets physics hell, all happening inside a space the size of a glove.
That is the analogy. And that is why it has been the bottleneck for the entire industry for decades. And that's why the source makes the claim that once you solve the hand, you have effectively solved the robot.
Really? The rest is easy.
Not easy, but the rest, the walking, the battery systems, the vision, are largely solved, or at least solvable problems with existing technology. The hand is the final boss.
That really puts into perspective why some of the competitors, like Boston Dynamics, haven't taken over the world yet. I mean, we've all seen their robot, Atlas, doing backflips and parkour for 10 years now. It's incredible to watch.
It's a marvel.
But it's not in my house folding my laundry.
And it never will be. Atlas is a marvel of dynamics. It can balance and move in ways that are breathtaking. But it's hydraulic.
It uses fluid pressure.
Right. It uses high-pressure fluid pumped through a complex network of tubes, and that's what makes it so incredibly strong and fast. It's why it can do those explosive backflips. But it's also incredibly loud, it leaks oil, it requires massive amounts of maintenance, and it is brutally, brutally expensive to build.
You can't mass manufacture it.
You cannot mass manufacture hydraulics the way you can stamp out electric motors.
Oh.
It's the difference between a hand-built Formula One car and a mass-produced Toyota Camry.
And one of those changed the world.
Exactly. Tesla looked at this problem from day one and said, it has to be fully electric, and it has to be manufacturable like a Corolla. They are not trying to build the most acrobatic, back-flipping robot. They are trying to build the most producible robot.
And that leads us to what the source calls the Tesla counterweight.
Yeah.
We asked the question earlier, if this problem is 200,000 times harder than a car, why on earth does Tesla think they can solve it by 2027?
Right. What gives them the right to be so confident?
And the answer seems to be that they're kind of cheating. Or not cheating, but borrowing heavily from their other business.
They're using arbitrage. They're arbitraging their massive investment in solving self-driving cars.
For starters, they have the data.
Billions and billions of miles of real-world video data from their vehicle fleet. That teaches the robot's neural network how to see and understand the messy, unpredictable real world.
They also have the chips.
The FSD computer, the Dojo supercomputer. They don't need to wait for NVIDIA or Intel or someone else to design a super efficient, low-power AI brain for the robot. They already designed it for the car.
And obviously they have the batteries.
That's a given. But the biggest single asset, the one the source really, really leans into, is this concept of end-to-end neural networks.
Okay, you have to define that for the listener who isn't a full-time AI researcher.
Okay. Old school robotics, the kind that's been used for decades, was all hand-coded. You had engineers writing explicit rules. If red ball is detected at coordinate X, then move arm to coordinate X, then close gripper by 40%.
You're manually programming every single step of the behavior.
Exactly, which works great until the ball is pink or the lighting is a little dim or the ball is slightly squashed. The code is brittle. It breaks easily.
It can't generalize.
It can't generalize. End-to-end means you get rid of all that code in the middle. You just show the AI a video of a human doing the task. The AI looks at the raw pixels from the video camera, what the eyes see, and it directly outputs the electrical signals to the motors, what the hands do.
There's no human-written code in between.
None. It learns by pure imitation. It's literally monkey see, monkey do on a massive scale.
So to teach the robot how to fold a shirt, you don't write a million lines of code about fabric physics. You just have a human fold a shirt 500 times while the robot watches, or while the human wears a data capture suit.
Precisely. And now ask yourself, who has massive factories full of thousands of people doing repetitive physical tasks, 247, that can be used to generate all of this training data? Tesla. Every single worker on the Model Y assembly line right now is, in effect, generating the curriculum for the Optimus robot that will one day work alongside them or even replace them.
That is a formidable and slightly terrifying feedback loop.
It's an incredible competitive advantage.
Okay, let's pivot. Let's get to the timeline. This is the real meat of this deep dive. Musk lays it out. 2027, 2028, 2029. Let's walk through these years one by one and really try to visualize what they actually look like.
Let's do it. Let's start with 2027. The claim is begin to transform things.
Okay, so what does that mean? Does that mean I'm going to have a robot butler bringing me coffee in 2027?
Almost certainly not, no. The source describes 2027 as the year of controlled deployment. I want you to think boring but incredibly profitable.
Boring.
The robots stay inside the fence. They don't leave the property.
So they're only working inside Tesla's own factories?
Yes. They go to the gigafactories in Texas, in Berlin, in Shanghai. And they start by doing the jobs that are the most repetitive, the most dangerous, or just the jobs that humans hate the most.
Like what? Give me an example.
Material handling. Taking a heavy box of parts off a pallet and putting it onto a conveyor belt. Or moving battery cells from one station to another. 8 hours a day, 3 shifts a day, no breaks, no sick days, no repetitive stress injuries.
So it's the internal beta test, but at a massive scale.
It's the ultimate proving ground. But the transformation part is real because it immediately changes the unit economics of building a car. If you can replace, say, $30 per hour human labor with a robot that costs maybe $3 per hour in electricity and amortization,
The cost of the car plummets.
it plummets. The transformation happens on the company's balance sheet long before you or I ever see one in public.
Okay, so 2027 is internal. Then we get to 2028, the claim. Be obvious.
This is the year it breaks containment. This is the year of the leak, the year of the viral video that isn't from Tesla's PR department.
So this is when we see them outside of Tesla.
By 2028, the source suggests the robots are reliable enough that they might start moving into tightly controlled pilot programs with trusted partners. Think logistics companies, warehouses.
Like Amazon fulfillment centers.
Possibly. Or maybe just general logistics and supply chain partners that already work with Tesla. But the source also teases something here that I found really fascinating.
What's that?
It's this phrase, converting unpaid domestic labor into GDP.
Wow, okay, that's a heavy phrase. Let's unpack that.
Think about all the work you do at home every week. Washing the dishes, folding laundry, cleaning the floors, mowing the lawn. In strict economic terms, all of that is unpaid labor.
Right, it contributes $0 to the official gross domestic product. It's invisible to the economy.
But it costs you something very valuable. It costs you your time. It costs you your Saturday morning.
And my entire Saturday morning.
Exactly. Now, if you buy a robot to do all of that work for you, suddenly that labor is monetized. You bought a machine, which is a GDP transaction, and you're paying for the electricity to run it, another GDP transaction. The source suggests we might see the first limited home beta units in 2028.
For the super rich, the early adopters.
The same people who bought the first Tesla Roadster for $100,000. Or the first Apple Vision Pro, the YouTubers and the tech enthusiasts.
And that's where it becomes obvious to the general public, because it's not a CGI demo anymore. It's real hardware in a real home doing real chores.
And your neighbor might have one.
And then 2029, massive impact.
This is where the curve goes vertical. This is where the age of abundance argument really kicks in.
The source brings up a really interesting concept here, the von Neumann machine. This sounds like something straight out of science fiction.
It is, but John von Neumann was a real and brilliant mathematician and physicist from the mid-20th century, and he proposed this idea of a universal constructor, a machine that is capable of building perfect copies of itself.
Self-replication.
Self-replication. Now, think about the implications of that for a second. If an Optimus robot can work in a factory, And that factory's job is to build more Optimus robots.
Eventually, you have robots building robots.
And then you have robots mining the lithium and the iron to get the raw materials to build the robots.
You close the loop.
Once you close that production loop, the only constraint on economic growth is raw materials and energy. You are no longer constrained by the number of humans in your population. You can literally print labor.
Printing labor. That is a terrifying and exhilarating phrase all at once.
In 2029, the source envisions production numbers scaling into the hundreds of thousands, maybe even millions of units per year. This is where you get what they call labor multiplication.
Not just labor efficiency.
No. This isn't just making an existing human worker 10% more efficient by giving them a better tool. This is adding a second, third, 10th worker who didn't exist before for every human worker on Earth.
This has to lead us to the economic shockwaves. I saw a term in the source that I just love. Flexible capital.
This is the killer app. This is the core concept that explains why this form of automation is so different from anything that has ever come before it.
Okay, so explain the difference. What's the old way fixed capital versus this new flexible capital?
Okay, let's say you run a bakery, you save up, and you buy a massive $50,000 industrial dough mixer. That machine is fixed capital.
Right.
It mixes dough. It is brilliant at mixing dough. It cannot frost a cake, it cannot sweep the floor, and it certainly cannot drive the delivery van. If, for some reason, people stop eating bread, that $50,000 machine is now just a big pile of scrap metal.
It's a sunk cost. It's a one-trick pony, and its trick is no longer valuable.
Exactly. Now imagine a humanoid robot. That robot is flexible capital. It has 2 arms, 2 legs, and 2 hands, just like a person. Today, its job is to mix dough, but tomorrow, your business pivots. You download a new software app, and now it's an expert at frosting cakes. Okay. The next day, demand drops, so you have it spend the day painting the walls of the shop or mowing the lawn out back, or even better, you rent it out to the construction company next door for the week to carry drywall.
So the hardware's generic. It's the software that defines the value at any given moment.
Precisely. Labor becomes software. And this is the mind-bending part. Capital investment becomes almost risk-free. Because if your bakery business fails, you don't have to sell your specialized dough bot for scrap. You just sell it on the open market to any other business because it can do anything a human can do.
This just completely breaks all of our traditional economic models. Though the source mentioned some speculation about sustained 10% GDP growth.
Which is a number that's it's unheard of for a developed economy. We fight tooth and nail to get 2% or 3% growth a year. But if labor truly becomes a scalable infrastructure, just like cloud computing did for software, then you could see a productivity feedback loop that we have literally never seen in human history.
It also forces a total rethink of something like Tesla's valuation. Wall Street is always fighting over, is it a car company? Or is it an energy company? Or a tech company?
And if this timeline holds, cars become a side hustle, a rounding error. The total addressable market for physical labor is, well, it's the entire global economy.
It's everything.
It dwarfs the car market. It dwarfs the energy market. If Tesla manages to capture even, say, 10% of the global market for physical labor, the valuation numbers just stop making sense in our current framework. They go into the multiple trillions, and they don't stop.
But this isn't just about money or economics. The source has this whole section called civilization engineering. That sounds pretty grand.
It is. It's about pulling back to the bigger lens. It draws this fantastic contrast between robotaxis and humanoids.
Okay.
Robotaxis optimize transportation. Humanoids optimize civilization.
And that's because our entire civilization is built by and for hands.
That's the core of the tool use theory. Just look around you right now. Door handles, coffee mugs, steering wheels, power drills, keyboards. Every single object in our built environment was designed to be gripped, held, and manipulated by the human hand.
We shaped the entire world to fit us.
We did. So if you want to automate that world, you have 2 fundamental choices. Choice A is you rebuild the entire world.
Smart doors that open themselves, smart roads, smart factories designed with no humans in mind.
Right, and that would cost quadrillions of dollars and take a century to retrofit everything.
Okay, or there's choice B.
Choice B. You build a robot that fits into the world we already have.
You build a robot with hands.
You solve the hand, and you unlock the entire existing workshop of the species. You don't need to redesign the factory. The robot just walks in, sits down in the human-sized chair, and pushes the human-sized button. It picks up the standard DeWalt drill you bought at Home Depot and uses it.
This has to have massive geopolitical implications, too.
Yeah.
The source mentions reshoring.
This is the potential death of globalization as we've known it for the last 50 years. Why do we manufacture, say, cheap plastic toys in China and then ship them all the way to the US?
For the cheap labor. It's a labor arbitrage.
It's all about labor arbitrage. But what happens if the cost of labor becomes the same everywhere in the world? And that cost is just the price of the robot plus the local cost of electricity.
The arbitrage completely disappears.
It vanishes overnight. You no longer have any economic incentive to ship goods across the ocean. You just build the factory right next to the consumer. Supply chains don't get shorter, they collapse into a single point. Manufacturing becomes local again.
The source even takes this a step further and changes the calculus for space exploration. It talks about Mars.
I mean, this is Musk's ultimate endgame, right? It always comes back to Mars. You want to build a self-sustaining city on Mars.
Right.
You can't just send 10,000 humans there to start digging ditches and building habitats. The radiation, the life support, the food, the psychological toll, it's practically impossible.
Humans are fragile, biologically expensive.
Humans are divas. We need oxygen and water and specific temperature controls and entertainment. Optimus just needs a solar panel and a firmware update.
So you send the robots first.
You send the von Neumann fleet first. They land, they deploy solar arrays, they start mining the ice for water and fuel, they 3D print the habitats, they build the city. Then, and only then, when the infrastructure is ready, do the human divas arrive.
So the robot is the pioneer, the scout.
The robot is the essential precursor to making life multiplanetary. It's the biological bootloader for humanity.
It is absolutely breathtaking when you zoom out to that level. I mean, we started this conversation with a single tweet about a timeline for next year, and we've ended up terraforming Mars.
That's the nature of exponential technology, though. The curve looks flat, flat, flat for a very long time, and then suddenly it's a vertical wall. What Musk is claiming is that we are at the knee of that curve right now, today.
So, okay, let's bring it all the way back down to Earth for the listener. Sitting here in 2026, what should they be looking for? Not the hype, not the flashy videos, but the real signal.
Ignore the dancing, please. Ignore the stage demos with the cool music. Look for the boring stuff.
The boring stuff.
Yes. Look for job postings on Tesla's website for actuator manufacturing engineers or high-volume robotics technicians. Look for supply chain announcements about rare earth magnets or custom gear suppliers.
The infrastructure.
And look for videos of the robot doing something incredibly mundane, like sorting a bin of mixed screws into different piles and doing it for 20 minutes straight without a single failure.
Reliability over flashiness.
Precision over power. If you start seeing that kind of boring industrial-grade reliability, then the 2027 timeline isn't just possible, it's probable.
I want to leave you, the listener, with one final thought that the source brought up.
Yeah.
He goes back to that age of abundance. If this all works, if we truly create a world where physical labor is no longer a scarce resource, what happens to human purpose?
That is the ultimate question, isn't it? For centuries, we have defined ourselves by what we do. What you do for a living is often the very first question we ask a new person at a party.
So what happens when the answer for almost everyone is, I don't have to do anything? That feels like it could be a massive crisis of meaning.
It's a luxury problem for sure, but it's a profound one. We would move from a society that is fundamentally organized around survival to a society organized around choice. And frankly, choosing what to do with your life when you don't have to do anything might be a much harder problem to solve than working a 9-to-5 job.
We are definitely going to have to do a deep dive on post-scarcity philosophy one of these days. But for now, I guess we'll just be watching the hands.
Watching the hands.
Thank you for joining us on this trip into the very, very near future. It's going to be a wild 3 years.
Indeed it will.
This is The Deep Dive. We'll see you next time.